Okay, so we have this condition of optimality, but we said we can unfortunately not solve it. We cannot write down an explicit solution. So we can do some gradient descent, or then, depending how you implement it, stochastic gradient descent. Right, and so what does this, what do we do? We start with some W0, some starting point, hopefully somewhat intelligently chosen. And then we're having our standard recursion at time t. When we are computing the next weight, t plus 1, we're going some in the direction of the minus the gradient. Right, so we're going in the direction of, in the minus direction or in the opposite direction of the gradient, and we're going a particular constant gamma t towards it, right? So, sorry, I'm going to try to write larger. I just tried, okay. But so, starting point, and this is the standard recursion that we have written down many, many times, a generic recursion of gradient descent. And since we know that the function is convex, we can be hopeful that we actually get to some, something close to the optimum value. Okay, so in principle, this would be fine. But let's take this as an excuse to talk about another way of doing it. And, it's something fairly natural. The second way of doing it is simply to use the second order. Okay, gradient descents, all we're using from the function is the derivatives, right? But we could also try to use higher order derivatives. And so what is the basic idea? Well, the basic idea is the following. If I'm sitting somewhere at some point w star, okay, I'm just writing star because I need a w, right? Then, at some w star, and I want to evaluate what the function should be, or approximate what the function should be at some w, then, of course, this is also now, of course, then this is also close to the constant term, right, wherever my starting vector is. Then I have the derivative. Okay, so I have L of w times w minus w star. And then I guess I need to take the transpose here, right? So this is the first order, the linear term, the linear approximation. And then I have plus w minus w star times the Hessian, so the second derivative, times w minus w star, and then I have here a transpose, right? So this is just the Taylor series. All I'm writing down is Taylor of order 2, right? Taylor series of order 2. Now, of course, we are in high dimensions, so it's hard to, to say or to visualize this. But if we were in just, in one dimension, then it simply means that I know the function somewhere here, and now I expand this function to second order. So maybe I'm somewhere here. I'm sitting maybe here at my w star. And now I'm expanding this function to second order around here. And maybe that's the expression. And so now that's, of course, an approximation, right? Because I would have to add all the other higher order terms. So that's only approximately true. But if I assume that I'm already close to the actual minimum, and I'm only interested in the function value close by, then it might make sense to take that, to assume that this is an equality, so that it's exact, right? And if this was exact, then what should we do? Well, if this was exact, then we should simply take this expression to be 0. This expression to be the exact expression, and look for where this expression takes on its minimum, right? So what should we do? So if we now think that this is the exact expression, here, right? Then, then we should simply take now, look at the condition of optimality here. So it means we should take the gradient of this to look where that is 0, set it to 0, and then solve for W. Make sense? So let's do this, right? So this thing here is just a constant, right? If we're taking the derivative, it's 0, right? Now, so this is, sorry, this is, I should be a little bit more careful. This is W, this depends on W star. So this is at a fixed point. So this is also a constant with respect to the W, right? It's at a particular thing. So if I multiply this with this is just a constant. This goes away. So the only thing will depend this and this. And so if I take the gradient with respect to this expression, it's always the same thing. It's just an inner product. All I get will be this, right? So I'll get the gradient of the expression itself. This comes from here, right? Plus. And now, what is the derivative of such a quadratic form, right? I get twice the same thing. I get, if I take the derivative here, what's left is this. And if I take the derivative here, what's left is this. But these are both the same thing. So the half will go away. So I'll get this plus, and I get h of W star times W minus W star. Okay, and if I want to know now where that is minimized, right? So all I've done here is taking the derivative. It's basically taking the derivative of this function here. And now I'm checking where this derivative is 0. So that's the condition of optimality, right? And so then what does this mean, right? So I'm looking now, what is this W? So the W is where the minimum is taken on, right? So this means that the W is, what do I have here, is equal to, I have the, sorry, so I should write this, let's say, in here. Put the star here, right? And so now multiply by this, the inverse. Then I have, get rid of this thing here. And so now what do I have? W is equal to W star, okay? And sorry, it's W star minus h of W star minus 1 times this L of W. Okay, and so this is my condition of, yes?
Can you please repeat around what point do we make a Taylor approximation? So what is W star?
It's the Taylor approximation. That's the point where we are sitting.
Yeah, but what do we take as W star?
Wherever you are, right? So you're at some point, right? And you're trying to approximate this function. At some point, you're trying to approximate the function, and you're trying to go to something that's better, right? And so you're approximating the function locally around there as a function. So this is now a function of W. And you're writing this function as a function of W as in terms of parameters of the derivatives of W star, right? And now you're saying, let's assume that that's actually the exact function. If it was the exact function, then what I have is just a quadratic form. And of this quadratic form, I can actually find the minimum, okay? And so we now just found the minimum. So this would be now the minimum, okay? Given that I know what the function, where I am, and what the function value is, the thing, and what the Hessian is, and what the gradient is there, okay? And so now we're taking that as an inspiration for an algorithm. Now, of course, this was an approximation, right? So this is an approximation, there are other terms. And so it might be a little bit ambitious to assume that I can walk all the way to the minimum. So one algorithm would be now the following. I put here t plus 1. I put here t. So I put everywhere here t. What is the star? And I'm computing the new one. So I could say I'm at some old point, right? I take the old point. I go a little bit in this direction here, right? The difference is here that I have the gradient as usual, but I have here this factor here, right? This non-trivial factor, the inverse of the Hessian. And then this would give me a new value, right? And if this approximation was exact, then after one jump, I would be at the minimum, But of course, since I'm not exactly approximating the function, I have some errors in here. It's probably best if we don't jump directly to it, but only jump, a little bit in this direction. So again, let's pick a gamma t. Okay, let's pick a step size. And now the question is, how do you pick the step size, right? So presumably you pick something smaller than 1, and you go only a little bit in this direction, and then you go up. Right, so it's quite similar to the first order method, but we have here this non-trivial factor here, right? Beforehand, we didn't have that. We just went a little bit in the direction of the negative direction of the gradient, right? But now we're having this inverse of the Hessian in front. Good, so now if we want to do this, then we still need something, right? So we know we have written down, so what do we need? We need this, right? And this we already have. This is up there, right? We have the gradient. So what we still need is an expression. This only works if we can actually compute the Hessian. And so the question is, can we compute the Hessian? So let us try to do this. So let us write down the Hessian. And so let me just do the following. I start with this up here. So again, since these are many terms, let me just do this for one term. And then so let me call this lnw. So lnw will just be the Hessian of a single expression in this sum. Okay, so that I don't need to write everything. So this means ln of w will just be the nth term here, right? So this will be xn sigma of xn t w minus xn times yn. Okay, so it's just this one single term. And now if I could compute the Hessian of this, then I just need to sum this up. There might be a gain way, and we'll see there's a gain way of writing this down in a compact way as we have done this in the last line here. But right now, let's just see what this term is. Okay, so we are now interested in this. Sorry, this is already, this one was this, okay? So this is already the gradient is already this form. And so now we need to take one extra derivative. So let us again go through each of the two steps, right? So all these things are always derivatives with respect to w. What do we have here, right? The xn doesn't depend on w. It's just a vector of length d, where d is the number of features. This is just a scalar, but inside the scalar there's a linear function that depends on the w, right? And so this inner product gives us a number, and then we apply a scalar function. And then we have minus, this is again a vector here, this is a scalar here, but actually this one does not depend at all on w, right? So that's just a constant with respect to the w, so it means this one we can forget. Okay, so that we won't get any contribution from that. So the only thing we have is this thing here, right? So let us check that. So we have an xn, right? And this is component 1 up to component d, when we're assuming that there's d features. And so let's assume this is component I here somewhere, right? So this is of this particular vector, sorry, this is written smaller here. Of this particular vector xn, it's the ith component, let's say. And this thing here is multiplied by something that does not depend on the component. It's just a scalar, right? Each of these components here is multiplied by the same scalar. And so each of them is multiplied by the scalar. And this scalar is this, xn t times w, right? Okay, so now we have the derivative, right? The derivative of the original expression with respect to, if we're looking at the ith term of this gradient, that's just this x, the ith component of this vector x times this function here. Now we need to take still of this expression, this times this, we need to take again the derivative, but now with respect to the jth component of W. So this thing here is already the gradient, right? So the gradient is the derivative of the original expression with respect to the first component, second component, third component of W, right? And as we saw, we don't need to worry about this part here, right? This derivative has the following form. The ith derivative, so the ith derivative of the original expression with respect, or the derivative of the the derivative of the original expression with respect to the ith parameter of W, the Wi, is the x, the ith component of the x that we're looking at, times some function here that depends, a scalar function that depends on this whole expression here, right? We now need to take that and still take one more derivative of this expression, but now with respect to some other component, okay? Component, let's say j, right? Now, this one does not depend on W at all, right? So if we're taking the derivative, it's just a scalar times something that does depend on the W. So what will be now, if I'm now looking at the derivative of I and j, so I'm looking at the ith and jth component, what will I get? I'll get from the xn, I get the ith component, right? Plus the derivative of this with respect to the jth component of W, right? But what is the derivative of this? Well, I first take the derivative. We know that the derivative sigma is sigma times 1 minus sigma. So this is sigma of whatever is in there times 1 minus sigma of whatever is in there. I'll write it out later completely. Times the inner derivative, right? But what is the inner derivative of this with respect to Wj? Right? This is just, what is this? This is just the sum where I'm taking the, the kth component of this times the kth component of this, and the sum up over the k. So I'm now taking the derivative with respect to some particular j. The only thing that I'll pick up is whatever the constant is here, right? And what was that? That's exactly, sorry, I'm running out here of space. I write it down. It's xnj. Okay, so let me write this down a little bit bigger now because it's a mess. So the claim is that if I'm looking at the ith and jth derivative, that's exactly what's in the Hessian, the ith jth component, right? So if I'm looking at h ith j, but this is now just for this one component, I still have to sum up over all the other ones, right? That this is equal to xn, the ith component, times the sigma of x and t w times 1 minus sigma of x and t w times x and j. Okay, has this kind of nice kind of quadratic form. Yes, please. It's against? You're correct. I'll try, okay? I'm just running out of space and, the physical limitations. Okay, so I'll tell you again, okay? So this is x, the nth vector, the ith component. Then I have the sigma times 1 minus sigma, and the sigma always has the same argument. And then it's the xn, the jth component. Okay, important is that this is constant this doesn't depend on the ij, right? It's just a constant that I have. And so it's just the xni, the ith component, times the xnj. So if we're taking this part out, what does this matrix, how can I write this matrix in compact way in terms of the vector xn? Forget about this, that's constant over both. I have a vector, let's call it z, right? And now I want to build out of this vector z has some dimension. Now I want to build a matrix where the ith and ijth component is just the zi times zj. How do I build it out of the vector z? How do I write this? Right? I just write the product, but just not the inner product. I just write the other one. Right? So this means I can write this as xn. So I want now a product that looks like this. This times this, right? If I write the x like this times the x transposed, then exactly this will give me a matrix of dimension d by d, which is exactly what I want, right? Because they're d parameters, right? Which has components exactly these. So this means this should be xn times xn transposed times the sigma of xn t w times 1 minus sigma of xn t w. Okay, so up to summing, that's it. Let's maybe write this down on a clean board. So let's summarize that. So what we want to compute, let's write this down. What we want to compute is the h of w. You know, I'm counting on that you only remember the last part, and that was large, okay? So, you know, okay, so it's the sum. And now what we have, right, what we wrote down there is we want to do now the sum of these terms, and then just the sum of for the nth term, so the Laplacian here of the L of n of w, right? And we said that this thing here is equal to the following. And we just wrote it down here, right? So this is just the xn times the xn t times the sigma of xn t w times 1 minus sigma xn t w. And so we have now an explicit expression for this Laplacian. And now again, so what is this? Let's just take a breath here. This is just a scalar, right? So this is just each of these terms gets multiplied. And this thing here is a d by d matrix. So from every sample, I get a d by d matrix, which is already exactly the dimension that the Laplacian has, right? And I just take basically the Laplacian is the sum of things, the Hessian, okay? So the Hessian is just the sum of kind of Hessians for each of these terms, and then normalized or weighted by these factors here, right? So these are just the factors I have here. Now, can we write this again in a compact form? Doesn't necessarily mean it's any more efficient, but if you want to, you can write this again in a compact form. Let me skip now the details, but you can write this again in the huge data matrix. So just a second, I just want to get the dimensions right. So this is n by n. Then just need to make sure this should be n, this be d, n. So that should be a transposed. And then this is a, I should maybe, and this should be, so, if you want to, if you just think about it for a while, just stare at it, you will see that you can write it in this particular form, where this is the huge data matrix. This is the n by d data matrix, where the ith row is just the ith sample. This is the transpose of it, and then we have an S. And if you think about what the S should be, the S is n by n. It's a matrix that's 0 everywhere, except on the diagonal. And then on the ith diagonal, it's exactly this term that we have in here, right? This term sigma, it's exactly this term here, right? So if we're looking at the ith term here, or let's say the nth term, then this is exactly the sigma x and t w times 1 minus sigma. Okay? Now, the last part is not that important. It's just it's sometimes nicer to write it in a compact form. Whether or not it's then much easier to compute depends, because the S is a huge matrix, right? The S is an n by n matrix, and that could be much larger than the D, for example, right? So it might not even be very efficient to do it like this rather than just sum up the terms that we have over there, right? So typically the D by D matrix, D will be typically considerably smaller than the N, and so it might be just much more efficient to sum up the D by D matrices themselves rather than write it in this form. Any questions to this? We still have one remark for that, but any questions? So we derived the conditions of optimality. There's no closed form, but we know the function is convex, and something greedy local will work. We either take the derivative, we compute it what it is, we compute the gradient, and we do the standard gradient descent. Or if we are more ambitious, then we're taking the Newton method, right? So what is the trade-off? In the Newton method, we have to compute, this Hessian, which, supposedly is considerably more complex, depending on what exactly the dimensions are. But on the other hand, presumably, we have much faster convergence, right? The number of steps we need is much less, right? So now it depends. Some cases can be better, some cases can be worse. Depends if you implement in one machine, many machines, etc., right? But it is an option to use a higher order method. So just one final remark. If you look at this, then what can happen is, remember we had this case initially, if we have, for example, something where the data is actually linearly separable, right? So let's assume just in the one-dimensional case, we mentioned this already, let's assume I have a one-dimensional case, and I have some data, and I can actually separate it very nicely. Okay, so I have some data points here, I have some data points there. And now, what do I do? Well, my function to separate will be this sigma function here, right? This logistic function here. And so now there's many ways to do it that I basically get it perfect, right? I can take this, maybe even this will give me perfect, at the end, give me a perfect prediction, right, or classification. But of course, I could also take something that is much steeper, right? If I let the W, if I scale the W's, then what this will do is the slope, right? The magnitude of these W's have to do with the slope of the transition, right? And so, there's basically no limit. You could make the transition as sharp as possible. But remember what we did. The original function was something like sigma times, the y, and then there was 1 minus sigma times 1 minus y. Now, if I take this very steep, then it means that these function values here will be very close to 1 or 0. And then if I take 1 minus this, I'm going to take the log of things that are very close to 0, right? Because I take the log, for example, of sigma, and the sigma could be essentially 0. And it will be the more closer to 0, the larger I take this jump, right? And so then I take the log of something that's very close to 0. So this, there's no limit. This can go to minus infinity, and there was a minus in front, okay? So this means if I make it steeper and steeper, the function that I have, in this case, can go to infinity. And so since there is no limit, it means that the limit actually will be achieved when W scales to infinity. And so then, computation, of course, you will get trouble. It will make no difference anymore to the actual classification because they're all good. But if you simply run the algorithm, it will simply explode, right? And so one way to get rid of this is to not just take the cost function that we wrote down, right? I guess it's already, the one cost function that written up here, but just add at the end again a regularization term, right? Just add again lambda plus W, the magnitude squared of W. And now you will, can be sure if you pick the W lambda somehow in the right order that the actual minimum is not taken on when W goes to infinity, and you have something well defined. Okay, so this could happen when you actually run it, and so that's just a small trick. Okay, we're done early. I have nothing else to say. We stop.